I've asked myself many times, why is it that I'm still excited about computers? That's quite amazing.
It
I
is.
mean, after so many years,
It's crazy.
I'm still excited about it. Am I as excited about it as I was, at high school when I saw a computer for the first time? I guess so, yeah.
Wow.
Yeah, I guess so.
Imagine early days, bottleneck is computation. It is, how do we get the CPU to execute instructions faster? How do we get the CPU to be faster? And then I guess you get to a point where the CPU becomes fast, but then maybe there's another problem of going, it's idle. Like it's so fast that it's like, oh, now we need to wait for stuff. So now it's a little bit idle. So what do we do there? Okay, now we solve that in some, this is kind of a crazy question maybe. Can you walk through the history
Absolutely,
of the bottlenecks
I'd be happy to. Presenting a paper at a conference, because I used to say that presenting a paper at a conference, the best feedback you get is that people are going to ask you questions when you're giving your talk. Oh, I was thinking about, this problem. How do you solve that? And they ask a few questions, then they go back and sit down and are quite uninterested in what you did. Whereas if you go to a customer and said, I've solved this problem, wow, that's really, really interesting, right? You said, Per, it's not going to take so much time until they know who Per Stenström is.
Come on!
That got totally into my head and gave me so much energy.
Oh, man. That's incredible. Grandma is a freaking beast, man. What
Yeah.
an amazing
Yeah.
person. Wow. Oh, damn. Oh, that's unbelievable.
Fantastic.
Oof. I'm getting goosebumps. I can just feel.
No, I mean, that uttering of her has gone back to me many times. Really. Really. That meant a lot. Really, it meant a lot. So I continue. And the rest is history.
The rest is history. Oh, my God.
I'm going to meet these people again, right? In a month or so.
I had the great pleasure of sitting down and speaking with Per Stenström, who is one of the world's leading computer architects and literally one of the most famous computer architects coming out of Europe ever. He's made major contributions to computing, hardware, cache coherence, which we discuss in much more detail in the video, and is generally considered to be a legend in the field. But Per is so much more than that, which I didn't expect. I rolled up to Chalmers University in Sweden. I greet Per. He has these old retro jeans, pulled up to the waist, polo tucked in. He just looks like a guy who's seen it all, and that's because he has. But there's this really fun phrase that I'm going to steal, and it's, if you see somebody riding a unicycle, you go, wow, that's great. And you see a bear, you go, wow, that's fantastic. You see a bear riding a unicycle, and then you have Per. I cannot stop myself from smiling throughout the entire conversation, and it is because Per somehow exudes so much excitement himself that I cannot help but just ride the wave that is Per in this conversation. Normally I would say, I hope you enjoyed the conversation. Here I will very arrogantly state that I know you will enjoy the conversation, not because of me, but because Per just has a presence that is so amazing and so intoxicating. So without further ado, enjoy this conversation with legendary computer architect Per Stenström. The first thing I want to ask, usually when I do this, I go on a little bit of a 5-minute monologue to explain some weird problem I encountered, and I need your help to solve it. And we're going to do that too. But first, I just want to unpack a little bit of your own journey here, because you've been at Chalmers for like more than 3 decades, working with computer architecture. I'm a bit curious about how you started out, because I guess the landscape of computers look very different, when you started getting into this journey. And I guess the first question that I'm most curious about is, when was your first encounter with a computer? Do you recall the first time you sat down, got to play with an actual computer?
I do. That was at high school. So I had the luxury. I went to high school in Lund, which is a university city, and so they had a computer center, you could say, and the high school class was at an excursion at that computer center. And I had a chance to play with the computer and write some simple program, and I got totally, obsessed by it. This is really, really interesting. And then I forgot about it because I didn't get exposed for many years. Well, actually at high school still, in the last year we could choose like a project, and I decided to do a project on what is called Boolean algebra, which is, you might know that it is the mathematical foundation of how computers do calculations. And so I did that, and that was another step towards, But apart from that, my main interest was in physics and mathematics, and so I had decided to study that at university until someone told me, are you going to educate yourself to not getting a job? And so I got really shaken up by that, and maybe I could combine my interest in physics and mathematics with engineering, and so that the rest is history. I went to engineering school at Lund University, and the rest is history.
That's amazing.
Yeah,
that's really amazing. I love the first conversation I had was with Martin Hilpert at the University of Neuchâtel. He's a cognitive linguist. So we would speak, what is language? Where does language come from? And clearly language seems to be an invented thing, right? Like when you conjugate a verb, it doesn't seem like it's, from a specific realm that we discovered.
right.
But then I speak to Kevin Buzzard, who's a mathematician, and he speaks very fondly of the Platonic realm, that it's a discovery almost out there. There's whatever we know, and there's whatever is actually out there, so it's a discovery. So it seems like you balance the two, where like there's physics and math, which seems to be more on you're discovering whatever is out there, but it's not super applied. It's difficult to really match it to the real world. So computer architecture seems to be a bridge between the two. How would you describe that?
Yeah, and going back again to my basic interest in physics and mathematics, it's kind of weird that I ended up with a very applied engineering discipline like computer architecture is, because it's not very theoretic. In fact, as a scientist, I haven't made much use of my skills in mathematics because it's very trivial. I mean, the math you need is trivial, but you need to be very creative minded to do scientific contributions in computer architecture, which is also true for other fields. But I think that's... but to tell you the truth, I don't know why I really ended up in computer architecture. I went to engineering school. I'm basically trained as an electrical engineer, and my interest there was in control theory and electrical measurement technology, and then computer architecture. And then I think I have one memory from when I studied computer engineering as an engineering student. I was exposed to how a computer works, and I really dreamed about it. So I really had to figure out exactly, build my own computer to see how it worked. I think it was magic, You could by a list of instructions tell the computer what calculations to do, and it did it, right? That was pure magic to me, and so I built my first computer as an engineering student, and then that really kicked off my interest in computer architecture.
That's incredible.
Yeah.
Is your I guess one thing that was cool, I say back then, is that you could build your own computer and you could kind of understand all of the components. I guess you still can now, but if you're building an 8-bit computer, like the scale of it is just, it feels more like realistic. It feels like you can more grasp it in your mind because there's just fewer of everything, especially like transistor count. But now it's, I guess really my question is, trying to build one's own computer now, I guess you can still build a simplified computer now, but the idea of keeping like a computer in your mind, because I guess that's almost what would happen if you build your own machine, is like physically you can touch it and then you can see it in your mind because you've literally built it. But now because the chips are so crazy...
No, you can obviously not build it by yourself. But, so what the chip technology gives you is speed, okay? So if you don't care about speed, just the principles of building a computer, you can still do it. In fact, it's not that complicated to get a computer to do what it's supposed to do, although it would, if you would build it by yourself, it would be very slow. But the principles would be there.
That's remarkable as well, that the basic architecture seems to be unchanged largely over the years.
Yeah, pretty much. I mean, so what has happened is actually a lot of breakthroughs when it comes to push the speed of computers to faster and faster computers that today can do billions of calculations per second, each computer, and then you combine many of them so you can have, a multiplication factor of probably thousands or so.
I really want to get into this development in speed, like all of the Moore's law, Dennard scaling, like the entire kind of crazy, because I guess it must have been, actually, let me take a step back here. If you kind of go back to high school, Per, you get your first encounter with a computer. I'm curious, the experience that you have where you go, wow, this is magic. Do you recall anyone else around you having that? Did any of the other classmates have the same experience where they're like, whoa, or...
No, I don't. I don't recall that they had.
Why do you think you had?
Yeah, that's an interesting question. I think it. Yeah. No, I mean, I was in a fantastic high school class. In fact, we're going to meet in a month from now, celebrating the 50th.
That's amazing.
50 years since we graduated.
That's crazy that you guys still keep in touch.
And we haven't seen each other since then. And I remember, it was an exceptional school. It was supposed to be one of the better high schools in Sweden, I would say. So the students in my class, many of them studied medicine. I will learn more when I see them. I just know about two academics, two professors, myself and one in biology. Right? But I don't think there are more. But I was a very creative mind, I think. I got fascinated. It was the fascination. And there were no other classmates that had that fascination for computers that I had.
Interesting, because it seems to be like very classically, like it's a bug. Once a bug bites, once you catch the bug, you just dream about it. It's very difficult to let go of, but it's weird what makes someone instinctively gravitate towards that thing while everyone else can, like surface level, have the same experience. Like they're still interacting with the computer, I guess, fundamentally the same way that you are, but they don't have that magical thing of going, whoa.
No, so actually, when we're talking about that, that's still an unanswered question I have. Why do you get excited about a certain thing? I think it has to do with you have collected something in your past that made you excited about it, but I don't have an answer. But we can talk more about it later, but what ended up being the subject for my PhD thesis, and my advisor didn't agree with me, was something called cache coherence protocols. In fact, I was sitting and designing a cache coherence protocol when you entered the room.
30 years later.
and my advisor said, no, you're not going to do a thesis on cache coherence. That's boring stuff or something like that. And I didn't listen to him. And I think that's a good sign of someone that is going to be a professor one day. And I've used the notion of getting intellectually in love with the concept I got intellectually in love with, number one, computers that day at high school, and number two, intellectually in love with cache coherence protocols, the subject of my thesis, PhD thesis. And I don't know why. It's just like this fascination again about cache coherence protocols. How can you get fascinated about something so technically weird, right? But for some reason I did.
Can you explain cache coherence protocols? What
I
is
can. I can do that. That's a skill I've
That's a
adopted
skill
to
I've
explain
honed
difficult
over the-
things in simple terms.
All right.
Well, let me see how I easiest do that. Okay, think about 10 individuals sitting in 10 different rooms, doing their own stuff. And then you want them to collaborate. So they have a whiteboard in the aisle, in the corridor. And in order to communicate, they post-it, slip with a number. And then the other guys can go out and see what numbers they are thinking about. So thinking of a number 5, for example, and then they jot down 5 on the whiteboard, okay? And then they move back again. If they weren't doing that, then... And the whole idea is that to communicate so all of them think about the same number, okay? And so if they didn't have this whiteboard, then they would probably think about different numbers, okay? Now they can synchronize and getting access to the same number through the whiteboard, okay? And that's how a cache coherence protocol works. In order for many computers to collaborate in solving a mathematical problem, for example, then they need to agree on a certain number. And that's how the cache coherence protocol is the mechanism for making it possible to synchronize.
What's the equivalent here of the person in the room and then the aisle? What's that? Is the person in the room like an L1 cache?
The person in the room
lives
is
its
a
own
computer,
life?
right? And you have many computers, and the reason you have many computers is that you want to solve bigger problems, right? So you want to have many computers cooperate in solving this bigger problem, right? And that's
the computer in this case, is this like an isolated CPU? Or
an isolated CPU.
Ah, okay, so you have isolated
so
CPUs.
You combine multiple CPUs.
Interesting.
Yeah.
Okay,
and
wow.
that's how we build computers today. So a computer chip consists of multiple CPUs, okay, you could say.
Interesting. Okay, and what is the actual cache made of? Because I guess it's obviously not RAM.
Cache is memory, essentially, right? So it's essentially a way to store a number, okay? You can store a number. Each computer has a cache, and it can store its numbers there. And this cache coherence protocol is there to make it possible for the others to see the value in the other caches, right?
Okay.
Which would be an analogy to a whiteboard, in the corridor where you can go and...
Okay, so they share memory. So each computer, each
they
CPU
can
have
share
the ability to
right,
share memory. How does that differ from they all have access to the same, let's say, address space in RAM? What's the difference here?
So the reason you want to have... So first of all, a cache is needed so that cache memory is needed for each computer to not have to go outside to the memory, okay? Because that takes time.
Yeah.
So that would be very slow. So therefore, you have this local memory called a cache where you can quicker get access to information, right? Now, the cache coherence protocol, the challenge in getting that efficient is actually to only have to communicate between the caches when there is a change in the content of the caches. And in fact, my advisor thought that this was a solved problem, and I told him that it was not, because you can only solve it when you have a handful of computers, but we want to scale up the number of computers to hundreds to thousands. And how to deal with the cache coherence protocol in that context is not known. That was an open scientific problem, I claimed. And he was, for some reason, didn't get excited about it. That's why I invented the term getting intellectually in love with the problem, right? And so I stick to the problem. I got my PhD thesis. I got my own PhD students. They got very excited about cache coherence. So my first two PhD students did their thesis on cache coherence protocols.
It's amazing.
And then I said, enough is enough. I want to do other things. Right?
Finally want to
And the funny thing is that I still got PhD students. No, I want to make my thesis on cache coherence. And how could I say no? I had battled with my thesis advisor to get, get my thesis done.
That's incredible. Why do you think you stayed with the thesis? Why do you think you stayed with that idea of cache coherence? Is it stubbornness? Is it because you believed in the idea that for you is obvious that this thing would be immensely valuable? Is it, what do you think? Because I can see your advisor goes in, Pierre, this is crazy, don't do that, you're wasting your time. Like, either you are kind of crazy where you just go, I don't care, I do what I want, or you go, no, you don't get it, you can't see what I see.
So you open up an interesting avenue here, saying, why did I get interested in that, and what has formed my scientific interests? And it turns out that maybe that's why I got excited about computer architecture. The reason is that for me to get excited about something, there has to be some value in it, okay? It has to solve, a problem that is meaningful. So it's not just, as you suggested, an intellectually interesting problem, but there must be a value. So I've always picked problems where I believe there is a value in getting that problem solved. And cache coherence is certainly, that would be an enabler for building bigger computers, right? Because if you can solve cache coherence for larger number of computers, then you can build bigger computers with more compute power, right? So there's certainly a value in that. And that has been how I have my mindset in solving problems. And I don't know the real reason, but one reason could be that after I finished engineering school, I didn't immediately jump on the PhD training train. I got it right there. Training. Oh, wow.
I love small clips like that.
I actually took a job in industry. And I think that formed me. I got exposed to, what makes sense to build that customers will like and stuff like that. So I got that dose of, realism into my blood. And then I got bored simply by, working in industry. It was not too,
intellectually stimulating. It was too
stimulating for my brain. So I went back to school and did my PhD. And probably I brought that with me to, that was how I choose problems to work on.
Yeah, because it's a bit funny. What I would love to maybe double click into there is, so you say you choose problems, or the ideas that end up occupying space in your mind are things that seem valuable and meaningful. And I think it's fun to unpack what is value and what is meaning in this context, because you do study physics and mathematics, and a lot of mathematics obviously is zero applicability.
Sure.
So that's also, and you could argue that that's meaningful as well, just in a weird, non-applicable, human direct equivalent type of way. So I guess the question is, how would you flesh out what is value and what is meaning? Is it that there's a direct impact on humans, like humans, their existence in some capacity are improved, more computers, more compute power, that translates to all of these different things that enhance the human experience at the end of it? Or how would you flesh out?
Yeah, well, it doesn't have to be, for me, it doesn't have to be directly, something that is useful for humans. Indirectly, it's useful for humans, but there must be a value in it for, products or something like that. Otherwise, I don't get excited. But I don't think it's meaningful for me to work on the problem. And on top of that, it has to be a challenging problem, of course. So when you ask me, why did I get interested in, mathematics? I think it was to train my brain. And I as a scientist, of course, I mean, I don't pick simple problems to work on. I pick problems that are a little bit challenging. Not too challenging, but challenging.
Yeah. The right type of
That's
balance
important.
between it's difficult enough that the answer doesn't fall out immediately, but
right.
you still know that the answer is there within reach.
If you don't pick challenging problems, there is no room for being a scientist because you need to publish it, and if you don't excite people in the scientific community, you cannot publish papers, and then you're pretty much dead as a scientist. So.
Yeah. No, I can see.
That's how it works.
What about then? You do mention this thing before of saying you study math and physics. I'm not letting that go. I can feel. And then you decide to go into electrical engineering and then computers later, largely sparked by someone saying you're trying to educate yourself out of a job, which is a fun comment. Suppose we live in like perfect utopia. Life is amazing. It's incredible. You don't have to work. You don't have to do anything. Maybe actually, let me take a step back. The Institute for Advanced Study, I love to harp on that one. I think that's always so fun. I spoke about that in a last conversation as well. But that, hey, Pierre, here's money for life. No responsibilities. Do whatever the hell you want. You can do math, physics, computer science, computer architecture. You can do whatever you want. Do you think you would still be doing computer architecture if we go back? Basically, the comment that your friend said doesn't exist anymore because there's no money. Everybody basically has free money. You don't have to worry about that because all of our needs are taken care of perfectly. Do you think you would still do physics and math? I don't know if my question makes sense.
Oh, yeah, it does. Well, that's a very good question. I don't think I've been driven by money ever.
Oh.
Well, of course, like any human being, need
I need
money
food
to survive.
I need a roof.
And you want to have decent life.
Yeah.
But money has not been so important to me. It has been more important what I do when I wake up, right? And a good example is actually, so I'm at the advanced stage that I should retire. I don't want to retire because I still have fun when I go to my job every morning, right?
Amazing.
When I go to Chalmers, I have a lot of fun. So I still, although, I would have a lot of meaningful things to do as a retired person. One big interest I have is music and playing.
Oh, wow.
Right? So it's so big, so I could have, if I could secure, again, if I could live out of being a musician, I would have done that.
Incredible.
As well as being a computer architect.
Wow.
But again, money has not been so important to me, really.
Incredible. That's so funny. I want to double click into the music part. That's so funny. I'm reading a lot about not a lot, but I'm reading through some of Plato's dialogues, and it seems that the ancient Greeks really believed that music was a fundamental part of having a virtuous mind and soul, that music is beauty, and it allows you to see and appreciate beauty in ways that are very difficult to do otherwise.
Pythagoras, most people only know Pythagoras because of the equation of
the right triangle and
the triangle. But actually, he invented the scale, the musical scale.
I didn't know that.
Oh yeah. So he was clearly interested in music.
It's incredible that
And
combination.
music and mathematics has been very tightly integrated, I would say.
So what does the music give you? Because I do think for a lot of people, it feels like if you are very technical into one of the sciences, I think computer architecture absolutely has one of the most technical fields. That means you have zero artistry. That means you are like, all of the performances and the arts, it's like, that's not what you do, because you're this, I sit in a dungeon and I sit and scribble my equations all day. But where does music come into the picture for you? When did you get interested in
It's a lot
music?
about emotion.
Yeah?
But I'm also technically interested in music, in composition and stuff like that, and find it very, interesting, to the structure in music, with the scales and the rhythm. So basically, the instrument that I've worked most with is actually drums. But I go beyond drums. I played a little bit piano, guitar. I played a lot of instruments, as an amateur. But drums I'm pretty good at. And that's the rhythm again, which is kind of, mathematical foundation of it. And I found it very exciting.
That's interesting. What is good and bad music to you? Is there any type of music where you go, this is incredible? And if you think so, why do you think that? What is it about that music that makes you go? Is it invokes?
I have a tendency to like jazz a lot.
Interesting.
And why is that? I think it's again creativity, and I mean with the improvisation and stuff like that, kind of. But I like, I have a broad musical interest. I can listen to classical music with a lot of happiness, and also modern music and stuff like that. So I'm quite. But I tend to prefer when the rhythm is a little bit more, it's not straightforward, right? So I like Latin rhythms a lot, for example.
That's so funny. That's really funny. Do you think...
It goes back to Africa and more complicated rhythm traditions.
Yeah. I like the... music is one of the fields where I have zero insight. I know literally nothing. So it's always weird for me. But it's weird for me then when people like you, who are very esteemed, speak about the properties of music and what it has, even the fact that you can approach it scientifically, that there's an actual foundation upon which you can theoretically go into it. Do you think music is something that everybody should just... It's difficult to always ask these questions, right? Because everybody should do everything almost, right? Like all things, history is important and religion is important and you should spend time on everything. But do you think music is something that would be beneficial for everyone to take some time to study, try to play an instrument, try to figure out what are notes, how do you, I don't know anything about music. But do you think it's beneficial for the development of a person to spend some time taking music seriously?
Ooh. I tend to say yes.
This is a computer hardware, obviously, podcast discussion, but here we
are. I
are.
also know that, not all people are interested in music, my mother was very musical, but my father, zero.
Oh, wow.
Absolutely zero.
What does that mean?
In fact, it was a funny story. He told me that, so his profession was, he was a school teacher at grade 4 to 6, okay? And in order to, at the time when he studied to become a school teacher, in order for him to become a school teacher, he had to be able to play organ. Why? Because every morning they were supposed to start with singing, right?
What a requirement!
Very crazy thing.
What a
and he struggled because
He hated
he
the
and
music.
the organ was not compatible. And so he trained the whole summer with he could play one melody, right? And then when he came to the test, the teacher told him, yeah, you're supposed to, I'm going to see how well you play organ. Yeah. And he said, I have one chance here to survive. Which melody do you want me to play? Choose whatever you like. Oh, yeah. Da, 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 da. And he played that single one.
It's the only one he had.
He had trained the whole summer. And he passed.
What a guy, the confident guy.
Yeah.
Okay,
I would never have.
That's a gamble.
About doing that.
That's a risky man. He was absolutely bluffing.
Well, that was
with
his
everything.
only chance, right?
Yeah. What do you want to play? I'll play it all. It's good. It's good. You're hired. But what was his relationship to music? Like, did he enjoy music, or was it? Because when you said he was zero musical, does that mean that he didn't enjoy music?
He enjoyed, actually. That's not fair to say that he didn't enjoy anything. But his register in music was very thin. And I never saw him excited about it. He got excited about when it was, lyrics, the lyrics that came with the music. That he liked a lot. But no, he was not really excited about music at all.
Okay.
But basically zero, and from my mother, it was a lot. So I think I got it from her.
Interesting.
And I have very early, memories from getting excited about music. I think the most prominent memory I have was with the Beatles. I was only 6 years old when I saw them perform in Royal Albert Hall, with the Queen sitting there and applauding.
Whoa.
Yeah, and that was so strong memory. I mean, of course, many people at that time thought Beatles were very cool, but that was...
That's a crazy memory, huh?
Yeah, it's a crazy memory.
That's nuts.
And then I got really excited about the drummer, Ringo Starr. And then I got my drum kit when I was 11. And I played drums for many years. Until I was probably 20 or so. Then we were forming a band, and there was a drummer, but there was no bass guitarist. I said, I can do that probably. That's related to drums. But I couldn't play. Well, I could play guitar, so it was kind of a step. And then I was practicing bass guitar 3 hours every day for 1 year.
Oh.
And I became a pretty good bass guitarist as well.
That's incredible. What about then? And we're gonna get back to computer hardware, but it's kind of funny to stay here. It's kind of funny to stay here. There's a thing that sometimes I run into where I think I'm very privileged that I find a lot of things like super fascinating. So I can stay with something for 12 hours a day, every day, and there's no fatigue because it's like playing a video game. It's genuinely just, whoa, this is crazy to get to explore. And then something I'll often run into from other people that have a more 9-to-5 life, if they say, lucky you found your passion, lucky you. And my hypothesis is, yeah, maybe, but... And this is the question that I want to pose to you, because when I listen to you, you go, drums are great, bass, what's it called? Bass guitar? I know nothing.
Bass guitar, yeah.
I know nothing about music. All other instruments, computer architecture, math, physics, electrical engineering, I am sure, jazz, I'm sure there's a bunch of stuff that you haven't even started to talk about, of things where you go, this is also extremely exciting. And then we can say, okay, maybe Pierre is just lucky that he just found, coincidentally, all 15 things that he loves. But to me, my assumption is, my conjecture is, this is probably the normal state of the human being. The human being is in a state of curiosity about everything, because there's adventure and mystery in everything. So the question isn't, wow, lucky you, Pierre, you found computer architecture, which was just the thing that you were born to do. It's more like everything is just exciting to me. Like, I can find beauty in everything, so that's why I pursue it. What's your take there in terms of, it's such a common thing that people do stuff they don't really want to do. They don't have a passion. If you ask them, what's the thing that you really want? They'll go, I don't know. I don't know what it is. Do you think it's some people are just, you're lucky you found the thing? Do you think it's a default state that we actually do want to be curious? Like that thing, what's your take there?
No, I think I'm very fortunate that I, as you say, and it becomes very clear now when we talk, that I've been driven by fascination about things. I think that's not everybody are like that. So that's a gift I have, and a gift that I've asked myself many times. Why is it that I'm still excited about computers? That's quite amazing. I mean, after so many years,
It's crazy.
I'm still excited about it. Am I as excited about it as I was, at high school when I saw a computer for the first time? I guess so, yeah.
Wow.
Yeah, I guess so. I still want to go to my job every morning, and as I said, I was working on a new cache coherence protocol, which is pretty interesting that I'm doing that. But yeah, so that's a gift I have, being fascinated about things, and that's driving my every day of my life, I think. And I would probably need many lifetimes to get fascinated into something else, right? and I never got it. I mean, I played music, but I could have certainly filled my life with that. Absolutely, and many other things too, I guess.
Is that a difficult thought? There's I don't know if you know who Anthony Bourdain is. He's no longer with us, but he's a very famous chef, a cook, and he had a cooking show where he travels the world and he explores all the different culinary scenes. And he has a quote when he goes to China, and he says it's so vast and so develops so rapidly. You could spend a lifetime devoted to just understanding it, and you still wouldn't even be close to having the full picture. And it's basically this. It's like the knowledge paradox almost. Like you could devote an entire lifetime to just a single field, to just computer architecture alone, and at the end of it, you still wouldn't capture everything. And then you have music, and then you have math, and then you have physics, and then you have philosophy, and just this thing of going. There's just so much knowledge all over, but I can't capture it because I just have this one lifetime. Like that thought, is that a depressing thought? Is that an exciting thought? Is that do you even think about that? Is it something that even enters your mind, that the world is so full of knowledge that we'll never be able to capture because we're just limited by time?
Oh, absolutely. Someone told me that it's not so long time ago that one person could actually host all the knowledge there is, right? But it has exploded. I mean, in the past 100 years, it's totally exploded. And I mean, you can look at scientific subjects get more and more specialized. Computer architecture is a very young discipline, and who could dream about that you could become a professor in computer architecture, let's say 100 years ago, obviously not, well, even 50 years ago. I mean, I don't think that would be serious thought about becoming a professor in a very specialized subject like that one. So, yeah, it's amazing.
And how do you deal with all of the knowledge that is out there that you will not be able to capture because of the time constraint? Like that thought of going, it's so fascinating, but I will not be able to capture all of it. That specific thought, what's your feeling there? What's your take?
Oh, absolutely, yeah. No, I mean, even in my, field, computer architecture, what has happened lately is, of course, it's very much driven by AI, right? Development of AI to do computations faster and deal with AI that is very demanding on computer resources in a more efficient way. And there's so much happening, right? I mean, the number of papers written, every week is enormous, So just to capture what's going on, you need AI, right, to structure the information,
synthesize everything.
Yeah,
Can you just give me the bullets, please?
Yeah. No, I mean seriously, it's amazing.
Maybe this is a fine segue to actually go back into computer hardware here. Do you recall, like, roughly when you started, like, really getting into computers? Maybe when you built your own, like, first computer hands-on. Do you remember when? Is this the 1980s, 90s? Do you recall when we are?
I would say 1979.
That's very specific.
To be very exact, yeah.
I love that. That's good. And I guess there's a bit of a magical period for like 20, 30 years where, like, almost year to year, the computers change so rapidly. I guess this must have been a pretty magical period. And maybe actually just to take a even bigger step back here, a computer fundamentally, because I think a lot of people don't actually know how a computer works, which makes all the sense in the world, because why would they? That's a very specialized thing to know, I suppose. But a computer largely is comprised of these smaller transistors, which acts as a switch, and they are comprised of silicon, which is where the semiconductor thing comes from. And the number of transistors, at least a modern take on the Moore's law, is that they double every 2 years. We just get more and more transistors for like decades. So the first question I actually want to give you here is, obviously memory is comprised of transistors. So like registers is comprised of transistors, even like RAM, DRAM cells is like a transistor capacitor. So when we get more transistors, it makes sense that we have more memory. Like we literally have more of the units that we can pack. And so it makes sense. How does that translate to speed? Why does a computer become faster just because we get more transistors? And I guess before you answer, if you could imagine that I asked this question like 25, 30-ish years ago, so before the Dennard scaling breaks down, because I guess when that happens, then there's a different route to increased performance. So while we're doing single core, why does more transistors give me better performance? How does that happen?
Right, so if we go back in time before year 2000, you could say, then Moore's law was very active, you could say, and gave you, as you said, twice as many transistors with every 2 years, you could say, biannually. And that translated into higher speed for two reasons. One is that you have more transistors to play with, then you can get more work done per time unit, okay? But also these transistors became smaller, then you could actually make them work faster, okay? An elephant doesn't walk as fast as, some smaller animal, right? Necessarily. Those were the two factors. But then we run into one wall, and that was that you couldn't increase the speed, okay? So then after the year 2000, the only, I wouldn't say it's necessarily bad, way of gaining higher speed was by doubling still the number of transistors. And then what happened was actually that we could combine multiple processing units on the same compute chip, okay? And then you double them every 2 years through Moore's law, right? And then you could get twice as much job done per time unit, meaning faster computers. Now, though, what has happened is that Moore's law, we cannot double the number of transistors that easily every 2 years. It takes longer time to double the number of transistors. So what we are doing now to gain a higher compute speed is actually to specialize the computers to be very good at, for example, AI, okay? So you specialize them, and that way you can run you can build faster computers. So that's what we're doing these days, essentially, to do faster. And it's very true that when you get twice as many transistors or twice as fast computers, I would say more generally, then you need twice as much memory. That's have a balanced system, you need twice as much memory when you have twice as fast a computer. So the amount of memory needed to have a balanced computer system, the amount of memory is steadily going up. Okay.
Oh, that's interesting. Okay, so the relationship between speed, how fast the CPU is, and the memory largely seems to correlate with a doubling of performance means a doubling of memory as well. Yeah. That's interesting. I didn't know that. What would be the good reason for that? Why is that obvious that has to correlate? Why do the two things have to go together? Is it just...
You could say that as you double the speed, computational speed, then you can grasp twice as big a problem. You can solve twice as big a mathematical problem in the same amount of time. And so you need to store that problem in memory. You need twice as much memory. That's a kind of a very simple, rough
Yeah, this seems to be like a good, not a heuristic. It seems more precise than a heuristic. But yeah, I can see that. But the faster you can go, the bigger the problem. The bigger the problem, the more data you need to store because it's fundamentally just a bigger problem.
That's the logic.
Okay, that's super interesting. Do you think there's going to be... Actually, let me just phrase this one. It seems to be... this would be a fun example. What are the different bottlenecks that are solved? Let's say each decade or whatever. I don't know necessarily how the bottlenecks develop over time. But I would imagine early days bottleneck is computation. It is, how do we get the CPU to execute instructions faster? How do we get the CPU to be faster? And then I guess you get to a point where the CPU becomes fast, but then maybe there's another problem of going, it's idle. Like it's so fast that it's like, oh, now we need to wait for stuff. So now it's a little bit idle. So what do we do there? Okay, now we solve that in some... Can you, this is kind of a crazy question maybe, can you walk through the history
Absolutely,
of the bottlenecks of...
I'd be happy to. So starting with actually the bottleneck sitting in the processing itself. So if we go back to, let me think, 1970, in the 70s, the computers that were built at that time, basically you did one computer instruction at a time, right? And it could be a very complex instruction that picked the number of data items from the memory, add them together and put the result back to memory again. But one such computer instruction at a time. Then that became a bottleneck, so people started to ask, can we do multiple instructions at a time? And there was two famous academic projects, one at Stanford and one at Berkeley in the beginning of the 80s, that had that as a big question. And the end result out of that was that you could actually, first of all, what they broke down was that before that, one computer instruction could take many time units to carry out. So you had to pick, one data item from memory, place it in the processing unit, put the other one, place it there, do the add, put the result back. That could take several steps, right? So what these famous projects did at Stanford and Berkeley, run by Professor John Hennessy at Stanford and David Patterson at Berkeley, was to be able to do one instruction in each time unit, okay? then after that, what happened was actually there were researchers asking, couldn't we do many compute instructions at the same time? Because, one instruction that doesn't add, use a set of data that is unrelated to another instruction that doesn't add. So why can't they do their adds in parallel at the same time? And sure, that was possible. So then the next step, was to do multiple instructions at the same time. And but that created a bottleneck. How can we find independent instructions? And so a crazy notion of doing speculative execution to find instructions in the future that can be executed started to unfold. But then the memory became a bottleneck, okay? To get, all this data at the speed that was possible to do all these instructions in parallel.
And just to pause this, just to make sure that I keep up here. So the conversation is, we can take one instruction, but the instruction is complex, so it takes multiple steps to be able to execute that instruction. And so the counterpart is to go, okay, what if we break down the instructions so they're so simple so that each instruction is basically just a single step? And then we say, shouldn't that allow us to execute multiple instructions?
Correct.
Because if I put two numbers to the ALU, or I need to load something from whatever, those are two instructions, but they occupy two different parts of the computer. So shouldn't I be able to do those in parallel versus, okay, here I load, then I wait, then I do this. So a lot of things are idle. That's the change?
Concept, yeah.
Okay.
You got it totally right.
Okay, that's cool. Okay, so what happens after that? Then you say, now we need to fetch stuff from memory? That's the next... okay.
Yeah.
Sorry, go.
Exactly. So then there was a lot of, first of all, if we rewind the tape, so the first bottleneck was actually that you need, as I said, you need more and more memory the faster, and more memory means slower memory, essentially, right? So you cannot have it, close to the processing unit on the chip. It has to be outside. And then it takes, essentially, the physics is such that, you need to go further away outside. It takes longer time, right?
What a weird trade-off, huh? You get a much faster CPU, so you need more memory, but more memory means slower performing. Oh, no.
Yeah, right. So how do we get out of that? Well, that was an interesting concept that actually came up quite early in the 60s called cache memory, right? And that's essentially a small, fast memory that you place close to the processing unit, right? But it's small. It must be small because you cannot have it big, then it cannot fit on the chip. It has to be small in order to be fast, right? And also to be close to the processor. But at the same time, we need all this data, right? And it cannot fit in that small memory. But there is a principle or an empirical observation called the locality principle, saying that the computer is typically working on a small set of data at a time, and for quite some time, so that you can have that small set of data in your fast, small memory, okay? So that the computer can get access to it fast, right? And so as you execute your program, you will slowly, go through all this data, but you will reuse it when it is in the small, fast memory, and that will gain speed. But, of course, eventually you will have to go all the way to memory and pick up a new set of data, right? And that becomes a new bottleneck now as we can execute multiple instructions and all that. And so there were a lot of, innovations happening with the cache memory as well. For example, one technique is called prefetching, where you actually anticipate I will need that data in the future, so I better launch, what is called a prefetch request to say, give me that data, and then you place it into your cache memory in advance, so when the processor needs it, it's there, okay? Those kind of ideas came up in the 90s, I would say. I was certainly contributing to that kind of...
That's amazing. Well, what's the mechanism that drives prefetching? How do you predict?
How do you predict? That's a very good question. So it could be that one idea that actually turned out to be a good idea was actually to... many of the computations are, you march through a data structure with same step for the next. So you access, for example, you have a long list of data items, and you could basically say, I pick the first item in the list, second item, third item. Oh, if I picked 1, 2, 3, then it's very likely going to be 4 next, right? And 5, 6, 7, 8, 9, 10. So I can start predicting, right? If I've seen a pattern, 1, 2, 3, well, probably you need 4 and 5 and 6 and 7, and then you start prefetching.
That's interesting.
That's a very good recipe for doing it, right?
How do you identify the patterns? Do you have like hard-coded patterns where you say these are the things that generally observe, or do you have an actual? What data the processor is requesting. Oh, you go for location 1 in memory, then you go for location 2. That's a computer address. You actually look up the data in the memory using what we call an address. That is essentially a number saying, I want to have the data at that particular place in the memory, right? And so you can build hardware that actually look at this sequence of locations, right? And then you can start predicting, what's going to be the next. I'm going to ask the stupidest question here. Where does that logic live? Does that live in the hardware? Is this like an assembly program that tries to fetch things like...
No, it's actually, you use your transistors, your fast transistors to do that, right?
Okay.
Yeah. So you build like you would do with all the computer hardware. For example, to add 2 numbers, you need circuitry to be able to add 2 numbers. Likewise, to do the prefetching, you need some circuitry that can monitor which locations
Interesting.
in memory.
Wow, that's crazy. So it's like a hardware implementation. That's nuts. Wow.
Right. So that's one way of doing it, but it's also the other way of doing it is actually to analyze the program before you run it on the computer. So a computer program is essentially a number, as we have talked about, the number of instructions, and you can analyze that and see also, in some cases, get the sequence is then known which locations in memory. Not always, but in many cases it's known, and then you can actually use specialized computer instructions that do this prefetching of data into the cache.
Okay.
That it will insert it as a part of the program.
That's incredible.
Yeah.
Okay. Okay. That's very cool. Okay, so prefetching is an actual hardware implementation that tries to predict based on certain patterns of behavior what the CPU requests. It tries to make a prediction as to these are the memory addresses we're going to be accessing next time, and so it fetches that into cache.
Yeah.
Okay. All right. So what happens after that? Because that seems to be pretty good. So what's the next bottleneck then? Or is...
Yeah, one bottleneck was, as I said, is cache coherence, as we talked about, right? That actually have multiple processors, and they need to solve a big computational problem. They need to cooperate in solving that computational problem, and so they need to be able to exchange results in a very efficient way. And they have their caches, and they're working the fastest way they can work is if they can find the data there, but sometimes they need to collaborate, and so they have to exchange data.
Is there a limit on how many CPUs can collaborate on a single shared cache? Can you put 100 CPUs that all have access to the same whiteboard in the aisle? Or yeah. Just parallelism is always like a fun thing, because it seems like
but that was an unsolved problem when I started out as a PhD student, right?
Yeah.
So I worked on that particular problem to make it be possible for hundreds of processors to share.
What was the unlock? What was the thing that allowed you to solve that problem, to go from, I guess, I don't know if cache coherence was a thing with, I guess your advisor says you can do that for 2 or 3 or whatever computers, but scaling that to hundreds of computers, what was the breakthrough? What was the thing that made that possible?
So one number of techniques that I looked at, one is to, so if you change data in one cache, then how do you let the other caches know about this change? You can do it 2 ways. You can say, you send out a message saying, if you are working on this particular data, then it's not valid anymore because I have the valid data. So you have to go and ask me, right? That's a favorite way of doing it. I instead said, why don't we send the data to these other caches, right? But to get that to work, it's you cannot do, if you do that too often, then you will create a lot of unnecessary overhead, traffic, as we say, overhead in the machine. So I smartly came up with cache coherence protocols where you can distribute new data very efficiently. That was one way of dealing with it. But I was also combining it with what we talked about, prefetching, okay? So you can, communicate data in a more efficient way. So I was playing with these kind of concepts as a PhD student, and also with my first PhD students. So we came up with a number of interesting concepts to solve that problem in a very efficient way. Right.
Okay. Maybe actually, I guess this also leads to a second interesting question. It seems like generally in academia, when you make breakthroughs, it's like good for you and you can get a nice award. I don't mean to downplay this. I think it's incredible. My point is more so, there's not that much overlap with a lot of like physics. You could argue it has to be kind of specialized for it to overlap to the real world, for industry to care about what it is that you do. You make some breakthroughs in, I don't know, number theory. Probably industry doesn't really care and go, oh, I will pay you a lot of money. But if you make an improvement like this, I can imagine a lot of very, very big companies are like, whoa, this is an amazing technology. We would love to have that. That there's this very interesting Venn diagram where computer architecture has academia and industry beautifully overlapped. Can you speak on that?
Oh, absolutely. I'm glad you asked. So what has been true with computer architecture is that the academic community and the industrial community has worked very closely with each other. So we basically, when you as an academic come up with a new concept, then you write a paper about it and send it to conference, okay? And we have a few conferences that are very influential in the development in computer engineering in general. And those are attended not only by academics, but also by, industrial people. So you quickly, if you come up with something that will have a huge impact, it will be certainly monitored by computer industry. So that has happened. I've certainly made some impact with some of my concepts regarding cache coherence, for sure. But more lately, I got really interested in. Yeah, that's a funny thing. I think we should open a new door here. Leaving cache coherence as one thing I've been intellectually in love with. So this is funny.
Let's see if we'll
Another
revisit.
thing I got intellectually in love with, and I know why, that was my first engineering job, okay? The first engineering job was to build computer hardware to produce synthetic speech, okay? So have computers really speak like human beings, okay? Quite challenging problem.
You built hardware to do that.
Yeah.
Okay, sorry.
Well, I use
continue.
computers. So I'm going to explain how I did it, okay? So there was a need at this company for a product that could, store human speech very efficiently in a computer, okay, and play it out, right? And the idea I had was to use what is called delta encoding to very efficiently store compute speed, because memory at the time was very expensive. It has always been, it was very expensive at the time. So you really wanted to store human speech very densely, okay? And the way delta encoding does that is that you have basically, if you look at, any sound, it will be like a wave, right? And so delta encoding will sample this, quite quickly, I think, at the speed. For human speech, if you do it like at 40 kilohertz, then that's good enough to store it pretty much exactly, because it's twice, 20 kilohertz is the highest frequency, and then you double it, right? And then you can sample it according to some theorem, okay? And what you do with delta encoding is actually you look at the last sample. Let's say that the amplitude was 2. Then if the amplitude of the next sample is 3, then you have an increase in amplitude and you store 1, a binary 1. And if it went down, you store binary 0. So for example, silence will go 1 0 1 0 1 0 1 0 1 0. But if the amplitude is increasing, it's going to be 1 1 1 1 1. If it's decreasing, it's going to be 0 0 0 0. Okay, so you got the idea, right? So you sample, dun, 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 and you get a sequence of ones and zeros, okay? And I found that very fascinating. So when I recorded, when I was speaking, I could detect that there was a lot of silence when you're talking. If you dissect, when you're speaking, the sound, then you would see a lot of silence, injected into the...
Yeah, in between the...
Yeah, and then you can store that as 1 0 1 0 1 0. You don't have to do that. You could say it's going to be silence for so many samples, and then you just you will record, silence for so long time, and then you play it out as 1 0 1 0 1 0 1 0. And then you have the vowels. Well, they are very nice because it's going to be A, for example, A is like a very regular kind of pattern, right? And then you do that also, you can record that very densely, okay? So I did those kind of obvious things, which I learned is what we call compression, right? Compress these kind of things. Now, that was a fantastic job, but the company actually didn't do well, so I have to find another job. And then I found another engineering job. I'm not going to tell you about that. I'm not going to bore you with that because it was so boring. So I said, enough is enough. I better go back to school and see what they are doing there. And then I found my advisor. He was building at the time what was called a multiprocessor system with many processors, which is products today, right? And I got really fascinated about that. So I became his PhD student. And my first question was actually, I would like to do research on compression technology. He said, wrong door. That's not my, favorite cup of tea. So if you're interested in doing a PhD with me, you better get excited about computer architecture. And so I did. But that idea of compression was
never left.
Was sitting there. And now I was a PhD student 84 to 1990, just to put this on the time scale. And then 1995 I became a professor here at Chalmers. 96 our daughter was born. And in 98-ish, must have been 98. I remember that I was reading fairy tales to her when she was supposed to sleep. And I did that every evening. And I found a lot of pleasure in doing that. But I also was that kind of guy that, well, sleep, you young lady, so I can run out and do some research, right? So I was, when I had read a couple of fairy tales, I was laying down and waiting for her to sleep. And then I was thinking about interesting problems. And then this idea of compression popped up. Why don't we compress data in memory? That would be a lot of value to that, because we could build theoretically much bigger memory, right? And we could bring data into the computer in a more dense fashion, meaning faster, okay? But of course, compression and decompression is a very slow process. So you will have to be smart about it, right? And, she's sleeping. I went up to my computer, started to do literature search, and there was not much done when it came to that. So I said, this is an excellent scientific problem to work on, right? So this idea of compression popped up again. My advisor didn't like cache coherence. He didn't like compression. And
what the hell is wrong with your advisor?
This must be a great thing, because I like compression. Cache coherence I had done, that was done. And industry had, got inspired by my work. And so this was the second one. And I started to have PhD student work on this problem, and we came up with interesting, fast ideas of how to do it. But it took until 2010 when I, together with a PhD student, his name is Angelos, came up with a really breakthrough when it comes to compressing data in memory. And we both realized that our ideas were so valuable, so we patented them before we published them. And then when he graduated, we created a company.
That's incredible.
0 Point
That's
Technologies,
incredible.
right?
Incredible.
Still going on. And that is world leading in compression technology, fast compression. What we're really good at is actually doing compression extremely fast. We're talking about decompressing chunks of data in a nanosecond, right? So that's super fast.
That is very fast.
Yeah. And the value of it is clear, right? We're talking about why do I get excited about things that has to be a value. Clearly here is a value because you can offer more memory capacity, right? more memory capacity, as I said, means higher speed.
Yeah.
Right. It translates into faster computing.
It does seem like extremely intuitive that would be wildly beneficial. But I'm so curious about the implementation details. We don't have to go into it, but I can see I haven't done anything on the hardware side, like the prefetching thing. My mind only goes, how would I write that in software? How would I write a program to do it? Like the fact that we do some of these things on the hardware level is, it's a complete abstraction to me. Like I know how the CPU and RAM and how these things communicate, but the other hardware implementation details there. When you do the compression, is that like, are you writing an actual software program?
No, that would not be possible. That's what people do, and that's why they haven't been able to apply it to memory systems. Okay?
Yeah, because I would imagine then my
you
instructions...
You have to do it, at the hardware level.
Oh man, that's so cool.
Absolutely.
Oh, that's so cool. Yeah, because I knew 0 point did something with compression, but I was like, okay, but I write a program, but my instructions, when I need to fetch them, live in RAM. So what do I fetch and then I compress? I was like, I can't get away from how do I move between the two and then compress? It was weird to me. But the fact that it's a hardware implementation, I don't know how it works, obviously, but it at least feels like it alleviates the awkwardness I had of trying to write a program that would do it, because I guess that is like a wrong approach entirely.
Oh yeah.
That's interesting. How does that? Can I do it on my Mac?
Essentially.
Can I implement what you guys have on them? If it's a hardware implementation, how do you, what type of machines, I guess, does that interplay with? Because I guess my MacBook is a closed system, so I cannot implement it here.
Yeah, so I mean, what we offer is essentially, you could say, electronic circuits that basically our customers are those that build computers, right?
Ah, incredible.
So they will take our circuits and inject them into the compute chip.
Amazing.
Sitting essentially close to what we call a memory controller that actually speaks with the memory. And so what happens is that this piece of hardware will intercept all the requests that go from the computer to the memory.
Amazing.
And basically say, oh, this data is compressed, it's sitting there in the memory, and we bring it in compressed fashion into the compute chip. We decompress it super fast and return it back to the processor or to the caches, you could say.
Yeah, that's amazing. Amazing. And how much does that increase? I say performance. I guess it increases.
So we can. It depends on the program, but roughly you could say a factor of 2.
Oh wow!
We make the memory twice
amazing.
as big.
Yeah. Wow, that's incredible. Okay.
Sometimes it can get actually more, and sometimes less, but on average.
Oh, that's incredible. Can you speak a little bit about the process of starting a company? I guess that's such a, like, you're going from, I feel like the idea, the becoming an entrepreneur is such a weird journey where you kind of go out there and you venture out and you have complete ownership, but you also assume total risk. It's just a weird, I don't want to say weird, it's a very big step to take, and it's so much easier to just play it safe and do what you've always done. So it's like such a, just walk me through it. Because again, when did you start 0 Point Technologies?
In 2015.
So you've been a professor here already for like 2 decades, and you've been into this, and then you go, you know what? Let's do this. Can you just walk me through the genesis?
Before that, I had been involved in some other companies, and also, to talk a little bit about, I mentioned that I, as an engineering graduate, started to work at a company, right? Before I went back to school and do my PhD. But then later, in the beginning of this century, in 2003 more specifically, me and my family, we moved to the US.
Oh.
So I worked for a computer company called Sun Microsystems for a couple of years. Actually.
Oh, wow.
First located in Silicon Valley, and then as a consultant for pretty much 4 years, I think.
Oh, wow.
Yeah. And then I actually got involved in a startup company here. And I've talked about my excitement for mathematics and physics, computer architecture, and music.
Oh
right?
no! What else? What else does he have?
My big another big excitement is actually, and I don't know why, but it's actually as an entrepreneur.
Huh.
The exciting things about getting out there with a new idea that can solve a very succinct, valuable problem for industry, and going out and talk to customer, that gives me a lot of excitement, really. So I love really going out there, and it's much more rewarding than presenting a paper at a conference, because I used to say that presenting a paper at a conference, the best feedback you get is that people are going to ask you questions when you're giving your talk. Oh, I was thinking about, this problem. How do you solve that? And they ask a few questions, then they go back and sit down and are quite uninterested in what you did. Whereas if you go to a customer and say, I've solved this problem, wow, that's really, really interesting, right? So, yeah, excitement, really.
That's so amazing. It's amazing, and I super agree with you. It's
so in the beginning of 0 Point, I was the guy going out to customers, and then
Oh, you were the salesman? You were the traveling salesman?
The guy,
You were out there with your MacBook going, or your computer going, let me show you how we're going
to
save your lives and make your lives better.
So I kind of kicked it off, right? And then we hired a CEO because I had work to do at Chalmers, right?
Yeah, no,
I couldn't
absolutely.
spend so much time. And I'm not so interested in doing,
like the operational day-to-day.
Building the company and all that kind of things. So exciting, but not so exciting.
Yeah, like the product is much more interesting. Solving difficult problems is where the uniqueness is.
I also like, what I really like in my profession that is totally orthogonal to what I'm doing is actually developing people, right? I realized not so many years ago that what's really the lasting value of what I do is not the great research with cache coherence protocols or cache compression, memory compression stuff. It's actually how I make people grow, right? That is true with the PhD students I have had over the years, which is I've graduated 23 to be exact PhDs.
Wow.
Over the years.
Wow.
Quite many. But it's also true for all the students that I'm teaching, my courses. I make them grow. And it was very true when I have been division head here at Chalmers. And the fun, exciting thing and the lasting value of that was actually to make colleagues grow as individuals. So making people grow is something that it's another excitement in my job, really.
That's so interesting. There was going back to the Institute for Advanced Study that I mentioned earlier, where it's the free reins. Here's a paycheck, do whatever you want. No students, no responsibilities. You don't have to do anything. Just do whatever you want. Obviously worked for some people, but Richard Feynman was very famously critical of that approach because he said he needed students. Just for selfish reasons. He said, me as a researcher, I need students. I need to interact. They need to ask me questions. And I've thought about those questions 100 times, but maybe they ask it slightly differently. Or maybe now that I think about the question again 5 years later from the last time I thought about it, maybe now it'll be different. But for him, it was, you need the students to be a good researcher. You agree? Or what's your take?
Absolutely.
What is it that you get from a student? Because my take here from what you said is there's a satisfaction that comes from your influence on them. You make them better in some way. But that seems...
But it goes both directions.
Yeah, I was about to say, because that seems to be the one direction you give them.
No. This is bi-directional.
What do they give you? How does Pierre become better?
Very simply, I plant ideas. When I get a new PhD student, I plant an idea, right? But it's not, very, well-developed concept. But I plant an idea, and That's exciting. So how do I get this? I, of course, have my favorite ideas that I would like the student to work on. But, you cannot force a student to work on a certain idea unless that student, he or she, becomes super interested in it. So I have to get the student excited about my
That's so interesting.
idea.
Maybe this is why you mentioned early on that this notion of what makes someone excited about something is so funny. Sorry, go ahead.
Super important. Otherwise, nothing is going to happen, right?
So how
that's
do you do that?
a process to start with to get the student excited. But the student is not going to tell you, oh, I got super excited about that. Because the new PhD student is very humble, right? Normally. I've seen, other characters that are not so humble. But most of the time they're very humble, right? So they're not going to tell you if this is an exciting problem or not. And I can give you an example. I mean, I can mention many excellent PhD students I have had, but one of them is this Angelos, who I formed this company with. And when he started as a PhD student, he's from Greece, and he's not a typical Greek person. He's a quite introvert guy. So he came to my office, and I started to plant these ideas about compression, and I gave him an assignment pretty much the first week he was a PhD student. And that assignment sounds like the following, right? Think of a cache that was smart enough to only store unique values. If you get,
Sure, like if
piece
there are
of
two
data
fives,
with
it's redundant, so rather store
5, 6, 5, you would only store
5 and
6
6,
5,
yeah.
but not the extra 5s, right? Now, my question is, how much smaller could we make that cache? Don't worry about how we would build it. That comes for later. First, we're going to see what's going to be the potential of that cache, right? So I said to Angelos, can you go back to your desk and figure out a way how we could, get a number of how much smaller the cache could be if we could somehow forget about all these redundant duplicates of numbers? And he looked at me and he was very shocked, I could interpret that he was probably thinking, that professor
He's
totally
crazy.
crazy, right? But
and he was right.
Tell him that. I cannot tell him that, right?
Cannot tell him that he's
so
right.
I better do what he asked me to do, and I go back to my desk. And I didn't see the guy for 1 month, for almost 2 months, and then he knocked my door and said, I think I have a number now to...
Oh, wow.
And he showed me lots of numbers, and they were really great. I mean, they were saying you could have a cache that would be 30 times smaller for one use case, 60 times for another, but it was like that automated. And I got so happy. You could see the number of boxes on, there have always been boxes in this room because although I don't move it. So I moved this office actually during the pandemic when I thought I needed a smaller room. But before that, I had a bigger room with more and more boxes, from things I hadn't unpacked. And what I did, I got excited about this number, so I took one of these boxes, placed it on the floor, and jumped on it, and it, of course, decompressed. Like this is how, we're going to do with computers. They're going to be compressed like this. Right? And I have his thesis over there, but if you read his thesis in the acknowledgement, he's going to say, and I still remember the day when I entered Per's office and he got totally mad and jumped on the box, in excitement.
That's amazing.
Right. And the rest is history, as we say. We had a lot of fun, came up with a lot of things, patented it, and then we created a company. And we're still, working on that company.
Yeah, that's so incredible. That's so incredible. The idea of how do you make someone else excited about something, it seems like you jumping on the box At least from the way that you tell it, just looking at you when you explain it, it doesn't seem like you're doing that as a attempt to try to make him excited. It seems like you, inside of yourself, have so much like passion for the thing. Like it's so fun. That you're like,
no, I think that is what I have contaminated my students with my excitement.
I was about to say, but it's real. It's authentic.
Yeah,
like it's genuine passion that just oozes
so.
out.
Yeah, I should have asked. I should ask them actually. What made you excited about the problem? I haven't done it, in a systematic way. I'm sure Angelos would say, yeah, you got me excited about that problem very early on. Right?
That's so interesting.
But again, going back to this, how do I get? So that's probably true. But I can the way because they're not going to tell me I got excited about this, right? But they start to work on it. And I know that they are excited because I can read that from their facial expressions. So I'm very good at interpreting facial expressions into emotions or excitement.
That's hilarious. You have the humble PhD student going, and Per goes, gotcha.
Yeah, something like that. Yeah, something like that.
That's so hilarious.
Yeah.
That's a really fun idea. One of my favorite ideas to contemplate, I think it's difficult to implement in practice. One of my favorite ideas about how do you get someone else excited, and even pertains to just knowledge. How do I get someone else to really understand something? Is the Socratic idea where he describes himself as a midwife. That it's already in you, like the passion or the excitement for something, the knowledge. It's already there. I just have to figure out how to help you get it out of yourself. I think that because this seems to be somewhat of an equivalency here. That the excitement for the problem is maybe already in him. It's dormant in some weird way, like a latent thing. But your excitement is the thing that makes his. So it's not like you give him the thing. It's that you somehow help him release it from himself. I don't know if the distinction makes sense, but it's there is something really.
Yeah, and I think that kind of excitement is also why I'm a fairly good teacher. The students like me. That's why I know that I'm doing, certainly an okay job. But I know when I enter the lecture hall, I'm full of excitement, right? And of course, that also, is transferred to the students. I said a couple of years ago that the day I'm walking into lecture hall and don't feel excited about what I'm going to teach the student in that lecture, I should stop teaching. And seriously, really. If I walk into a lecture hall and I'm not excited, saying, what am I doing here, they just occupy my valuable time, I should be out of it, right?
Incredible.
Seriously.
That's an awesome take.
Right.
Yeah.
And so I think that's probably, being a good teacher is actually, you're an entertainer. In the lecture hall, you're an entertainer, right? Really. And feel excited. If you are not excited about your subject matter, how can you believe the students are going to be excited about it? So you have to be excited. That might not help, though, but it's certainly a prerequisite for making the students excited.
Yeah, that's amazing. Has it been difficult for you to, because it seems like very classically, I think those two things of there's research and there's the theoretical work and there's problem solving and then there's I have to give knowledge to other people and make it entertaining, and like the two disciplines still seem like pretty like there's a pretty stark line between them. They don't overlap that much in terms of like, or maybe they do. Maybe it's like people who are extremely good at their work.
My feel is definitely that if you're not a good teacher, you're probably not a good researcher.
So you say the two go hand in hand.
Statement, but I might be wrong. So in fact. Whether it's true or not, but a person that I really found very exciting, John Nash. You might know about John Nash?
The mathematician?
Yeah.
Yeah?
Who got the Nobel Prize in economics, actually. Yeah, well, he was for many years, really sick in schizophrenia, right?
Yeah.
And then he came out of it, not totally, but... so he could start functioning again, and he got the Nobel Prize in economics. But there is this Beautiful Mind movie, Hollywood thing about his life. But there is one scene where he has to teach at MIT, and he walks into the room and say, "Oh, I hate this, and you probably have much better way of using up this time, and I certainly have much better way of using up this time than teaching you students," right? Things like that. So and he was an excellent scientist, obviously. And if that is true that he didn't like teaching, then I'm wrong, right? But I tend to think that, well, if you're going to have really impact of your research, you better like teaching, because it's a lot about communication, right? So, and I like to, talk about and explain in simple manners what I'm doing, right? You had me explain cache coherence.
Yeah, we did. No, it was very good, and you've explained a bunch of many other things.
So yeah, you get better and better in doing that, complex things. And I tend to say that there is not a sufficiently complex thing that you cannot explain in simple terms. You can always do that. If you really understand what you're doing, you can explain it in simple terms. That's my conviction, that it's like that.
Yeah, that's that seems to be universally true for any field. If you deeply understand it, you can
explain it.
Yeah,
through an analogy or something.
Exactly.
Like that, that makes sense to the audience.
Yeah, it's kind of funny. I remember also, speaking of, you mentioned Patterson earlier. I remember listening to a conversation with him. He said the exact same thing that you just said. He said, good teachers, good researchers, they usually go hand in hand. If you're a bad teacher, he said, at least anecdotally to him, it seems you're probably not going to be a great reaser either. So it's fun that he had the same take that you did.
Interesting to hear, yeah.
Yeah, it's super, super fun. One thing I would love to touch on here, if you go back a little bit to the development of hardware, because I think this is... all right, I'll try to give you how I end up at this question, because I think the road that I take to get to the question is also kind of a funky road. In math, you have the mathematician Paul Erdős, who has the concept of the book. The book is this thing that contains the most beautiful proofs that we have. These are the proofs that will live forever. In a million years, you will not have a better proof than this. So he goes, that goes into the book. So this is it. And I wonder if there's just something funny about, you mentioned that if you look at computer architecture, at least like the main components and how it functions, I could build a very primitive computer that still largely resembles how a modern computer works. It's kind of a crazy idea. So then I thought, does that mean that if we find aliens tomorrow and they have computers, will they have a von Neumann architecture? Will they have the same things that we do, because it didn't really change? And so I think that question is super weird of, is this the optimal architecture that we have? Does this go into the book of architecture that, hey, you have a memory unit that contains the data and it has the instructions, and then separately you have a CPU that's going to execute it, and that's just what the optimal computer looks like? You can't improve. I actually love to get your take. And before I get your take there's a fun quote that I want to read aloud here as well. And it is by John Backus, who is a Turing Award winner, and he says this like 50 years ago. He says, it seems like you already know maybe, but at least, yeah. He says, surely there must be a less primitive way of making big changes in the store than by pushing vast numbers of words back and forth through the von Neumann bottleneck. Not only is this tube a literal bottleneck for the data traffic of a problem, but more importantly, it is an intellectual bottleneck that has kept us tied to word-at-a-time thinking instead of encouraging us to think in terms of the larger conceptual units of the task at hand. So it also seems like most of the stuff we've been talking about is this thing of going, there's memory, how the hell do we get that to the CPU? We're just crazy clever about different ways to optimize that thing, but the fundamental architecture is still there. Is it? I don't even know where to start to tee this thing up. Like, I don't even know like what the specific question I should ask you here. Whether or not does a different architecture completely exist? Is it realistic? What we have now, is this the optimal form? Do we just keep finding innovations to the existing architecture? I don't know, take this wherever you want, I guess.
Well, we have to remember one thing, that it's not only the principles of how we do computations that matters to how we build computers. It's actually an interplay between that and technology we use to build computers. And the basic technology that we have used and are still using to build computers is semiconductors, okay? And so that's a foundation, right? I mean, for a principle, for example, von Neumann architecture to make sense, it has to be in harmony with the underlying technology. And it so turns out that actually the von Neumann way of building computers has made sense for the technology that we have been using for so many years to build computers. We have been able to build fast cache memories so that we don't have to, this bottleneck that really sits there with the memory doesn't really exist, because we can, with the help of the underlying technology, kind of go around the von Neumann bottleneck, as we used to call it. But things doesn't hold forever. I mean, I'm quite certain that semiconductors, we will not be able to push semiconductors much further than we have done. The basic reason for that is that if you look at the size of a transistor, it's down to on the order of 1 nanometer. That's only 10 times the size of an atom.
It's very small.
Which is 1 angstrom, which is 0.1.
It feels strange to speak atoms.
So, I mean, we are at the physical limit of semiconductor technology, how we can get more transistors and things like that. Human imagination is fantastic. I mean, so for many years they put the transistors horizontally like this. And then they say, why don't we build Trump towers like this, right? And then they switched it up. And then you could actually, since a transistor is tall and thin, if you raise it up, then you can press more transistors like that, right? I should actually do it like this. So that's a way to make it scale up more. So there are these kind of tricks that people come up with that we're going to see scaling happen for probably another 10 years. But at some point it's going to be, that's it, right? And then it's a matter of new technologies coming up. And then maybe other ways of doing computing will make sense. Well, one example is, of course, that there is a lot of attention to is quantum computers, right? Which is completely different principles of how to, don't ask me to explain because I'm not a physicist that is able to do that, but I know for sure that it's a completely different way of doing computations, right? Now, the problem with quantum computers is several-fold. There are still a lot of technological challenges to make it work meaningfully. That is solving, problems that classical computers cannot do. And then there is also a question about what is the sweet spot of computational problems that quantum computers are good at, that classical computers cannot do. So they will for sure not replace classical computers, but they might be able to solve problems that we cannot solve with classical computers. That is still an open kind of question, what those problems are.
Yeah, so a different computing paradigm that also probably targets a different set of problems that classical computers cannot. Yeah. What's the what would be the biggest limitation to you dropping everything you do and say, I'm going to try to create a completely new architecture from scratch that's going to not have, and you're right that right now the von Neumann bottleneck is circumvented largely by caches, cache coherence. There are all of these fantastic mechanisms that makes that problem shrink very much in significance. But if you were to say, scratching everything, blank slate, let me try to sketch up a completely different architecture. The limitation there is that there's so much development that has already been done that it's like, what's even the best way to put it? I don't even know if it's legacy, but it's like if you go to like a little bit up higher the software stack, you have like banks. All of banks, they use COBOL as a programming language. It's very difficult to switch because there's so much legacy. It's like the migrational workload would just be impossible to manage. And when I look at the hardware stack, I also go, there's so many different implementations. There's so much stuff here that scratching everything and say I'm just going to start from scratch feels like overwhelming. Like it's this. I don't know if the question even makes sense.
It does. No, I mean, that's a huge limitation. It's the legacy that you were talking about. That, I mean, even if you come up with, a fundamentally different way of doing computations, you have invested so much in the software system, so you better find a way to migrate that to the new compute environment. So that would be that is one reason that is hindering us from trying out completely new ways. But the other, and I mean, certainly thinking about, so one of we were talking about the von Neumann bottleneck, and that is a real problem for sure, because what happens today with the AI workloads is that they need an enormous amount of memory, and when you do this kind of computation, you need to move a lot of data into the caches. Do not work that well for AI workloads, and so this von Neumann bottleneck is really something that is gonna hinder us or become a real bottleneck. To counter that, one concept that I am looking at and others are looking at is what is called processing in memory. So you distribute the computational power, you put processing units inside the memory itself. And that way you could actually you don't have to move the data, right? Wow. But the problem is that you create a very distributed system, and to manage the data across all those processing units is not trivial, and still an open problem how you do that efficiently. But we might see progress in that regime to solve the von Neumann bottleneck for sure. So, I mean, human imagination is fantastic. I mean, we come up with new solutions to problems, and there are still a lot of open, interesting problems for young computer architects to work on. And I'm not going to say as my advisor.
Yeah, you shouldn't do that. Yeah, leave it alone. Right. I think it was Jim Keller, was obviously a very famous chip maker, designer, architect, who I think also said when people dismiss Moore's law every decade, it seems to be his take, when people very conservatively speak, Moore's law is going to die. And then he says, sure, but human innovation just keeps solving problems here and there, and they add up, they just accumulate, and then it in that way continues. It is crazy how clever humans are at just solving problems. It almost feels, not cliche-wise, but unless you run into a physical law, like this, just the physical laws just dictate, hey, this is transistor, this is as small as we can make it. If it isn't that, it really feels like humans can they'll figure something out. They'll do cache coherence to some crazy extent, and then they'll make it work somehow.
And another thought I would like to add on top of that is that, I mean, there are people today in the research community that are looking at alternative technologies for computing and completely alternative ways of doing computation. Now, I've never been so excited about that because it takes quite an effort to change the needle, to have the industry go in that direction. And as has been quite clear from what I've said, is that for for me to get excited about the problem, it has to be something that industry is, chasing rather than, something that no one is interested in solving. So I used to call that speculative research. Well, if all this is going to happen, then if you do research on a speculative technology, then that might have a huge impact. But I've never, been so excited about doing research in a speculative way. And I've seen too many, attempts to, there was not many years ago, quite many people in my research community that got interested in something called phase change memory, a way to build new memory technology, not DRAM, but a technology that could actually increase the capacity and being performance-wise competitive with DRAM, and at the same time also non-volatile in the way that if you switch off the power, you still have the data.
Sounds
there.
pretty
good.
Go
away, right? So that seemed to be, this phase change memory seemed to have a huge potential, but it never happened.
Interesting.
Because, legacy reasons and stuff like that. It never happened. But it was so close to being adopted. In fact, Intel and Micron, they invested huge amount of money into that, but it just didn't happen.
Wow, that's brutal.
So, and there were a lot of, people with, mindset like me that got excited about it. I never, did it, but I kind of just monitored what was
from the outside looking in, going, let me see what you guys are doing in case anything fun develops. Exactly. That's also a crazy thing. I've spoken about that in the past as well with, especially in mathematics, you dedicate yourself to a specific research problem that may or may not end up being fruitful. You may come up with something amazing and you may spend years, if not decades, on something that never yields anything. Right. And it's a weird human thing to be in. It's like an entrepreneur bears enormous risk if the company fails, but there's a weird type of risk in pursuing a research problem where the cost isn't, money or now employees don't have a job anymore. The cost is arguably more valuable. It's time. It's time that, and maybe I guess really what I'm trying to get into here is, what's the actual motivation for doing a research problem? Is it the process? Is it just sitting here working on cache coherence is extremely fun? Whether or not it works, jury's out, we'll see. But it's just the process of working on the research problem is fun versus the fun is that this thing actually works. It's the process is fine, but it's the payoff. It's when it actually works and I can see it and people use it. That's the fun thing. Where it seems like if it's output measured, it's I need this thing to work. If that's the carrot, then that seems extremely risky. Because if that doesn't hit, then you lost time, which is arguably more valuable than anything else. What's your take on that one? So
the real, payoff with research, in my view, is, when you make the discovery. A colleague of mine, a friend, I would say, in the community, told me that research is very much like shoveling, right? You shovel every day, you shovel to, and suddenly you find something very valuable there, right? But you also mentioned this, what if, you don't succeed in solving the problem, then you lose all the time that you have invested in it, you have lost, right? That's the risk management you have to do when you do research. You're trying to address problems that they should be challenging, otherwise you have nothing. If it's obvious what you do, then it's not research anymore, right? So it has to be, open problems. But when you're an experienced researcher, even if you don't see the solution, you can somehow get a sense of the risks. Well, I don't know exactly how to solve that problem, but I'm sure that if I sit down with it, then I'm going to sort it out. I heard one story, I don't know if it's a true story or not, but someone told me that he knew a mathematician that he was invited to give a talk at at a place like 3 months later. And then he thought he was going to present a mathematical proof at that time that people are very excited about, that hadn't been solved. And he hadn't made the proof himself, but he kind of had the intuition, I'm just going to sit down with it. And then it's going to,
it's going to fall out.
And I can put together my speech and go and get the people excited about it. And for some reason, he didn't manage to get it together. This stupid mathematics is actually, making a joke with me because it should work. Right? And he was struggling big time. I think he solved it in the last minute or so. But it was, his intuition was that it was fairly easy to get. Once he got time to sit down with it, he was going to solve it. And that intuition, after you have done research for a long time, which I certainly have, is quite strong. You have a good intuition of what are good problems to work on, right? And that's very important for your PhD students, right? I mean, that they are not, because they are supposed to get done in 5 years or so. So if they were to, work on Mission Impossible, that would be very sad, right?
Where do you think that intuition comes from? And actually, let me ask you a different question here. Because the first thing I thought of when you said that, because I do agree that intuition seems to be a very legit thing, and it seems to be something that just happens. You're not sitting here contemplating for 10 minutes and then I make a call. It's like I can just 30 seconds and I go, I know if this is a good or a bad idea. I kind of have we should follow this path. I can't explain it to you yet. I can if I sit down, but I just know this is the path, so let's go there. And that seems to be, I'm curious about what the underlying mechanism is. I
think the underlying part of it is that, to solve this problem, you need this knowledge, this knowledge, this knowledge, this knowledge. I don't know really how to combine it, but I'm sure that, these knowledge islands, if I combine them, then really I'm going to be able to solve that problem. Something like that, right?
That's so funny. Maybe
so
it's,
you have the best way of explaining it is that you have a rough idea of how to solve the problem, but certainly you haven't hammered out the details, right?
That's so funny. That's a good point. I'm working on something where I have like 1 million rows of data, and I need to figure out how do I aggregate that so I get to at least a couple of orders of magnitude less. And it's very critical for what I'm doing. If I can't do that, then the entire thing dies. And yet I feel pretty good because I have I kind of know what all of the variables that exist. I can I don't know exactly, but I know it's possible. So
that's right.
It's just, you're right. I have a rough idea. I don't know exactly how to connect the dots, but it feels like, I can kind of see that this should be possible. That's a fun thing. What do you think then happens when intuition goes sideways? I don't want to try to put any negative sentiment onto your advisor, but I would imagine that when you go cache coherence, when you go compression, that it's his intuition, and he looks at that and he goes, you're crazy, that's a bad idea. But it seems like both of those things became very big successes. So is his intuition just off? What's your take? And again, I don't want to necessarily put him in a bad spot, but what do you think it is that makes intuition go bad for someone that I assume has generally good intuition?
I think I can capture that with a saying that people have heard, the devil is in the details, right? It's when, the real challenge is not how you combine these, concepts, but rather, when eventually get it to work, right? You don't, there's, at the abstraction you cannot really appreciate the difficulty and the challenges that are in the details. The devil is in the details is something that can really make you fail when it comes to intuition, right? And I've seen that happen over the years quite many times. In fact, going back to something I talked about with Angelos, my PhD student that I've done 0 point with. So I mentioned that, his first assignment was to sort out what would be the benefit if we could have the luxury to only store each unique value once in a cache. And he came back with a number. That was the opportunity, right? And then the next thing we asked ourselves, well, let's build such a cache. Right? And my intuition was that it should be possible. Maybe we cannot get a factor of 30 in compression, but a factor of 5 or something like that would be quite possible. But it turned out to be a dead end, because in order to keep track of these unique numbers, you need some metadata that point you to those unique numbers. And it turned out, just to go and avoid going into all the details, that the amount of metadata to manage these unique values just exploded. Right?
Yeah.
So you, at the end of the day, you got all the compression opportunities that were there were just, going out of the window.
I love that. Yes, what a fun example.
That was, an example of where the devil was really in the details. Right?
Yeah, I love that. What a fun example. Work. Yeah, what a fun example. That's such a fun example. Yeah, because I could imagine that even the process going, how do we actually keep track of everything being unique? Okay, we need to separately have some way to do that. And then that thing separately starts to grow. And then you look at the actual potential upside that would come from this. And you can see that shrinks as the amount of data you need to actually make the solution work. Yeah, what a fun trade-off. Yeah, okay. But your point there is very good indeed, that there's the abstract, this should be possible. But once you actually get your hands in it, you go, ooh, these are things that were very difficult.
I hadn't realized that was really the bottleneck.
Yeah, that's
there.
Yeah, that's a good.
I'm actually working on a concept now, not with PhD students, but with myself, that initially I thought this is a darn good idea, right? But when I started to massage the idea, no, it doesn't work. And it's just where intuition says, this must work. And it just doesn't work. And I still haven't given up.
It's just amazing.
I need to probably look at the problem from a very different angle.
That's amazing.
Because I'm so sure there is something.
I love that so much. That's so good. I mean, but it's cool also that you trust your intuition so much that you know that there's something valuable here.
And you don't give up, right?
Yeah.
And many times it's just that you have the wrong approach to the problem. You have to look at it from another angle, and that's how I used to phrase. When I was a PhD student, I found myself into two modes of operation. One was probably, you could call it the crazy pair, and the structured pair. The structured pair was, very systematically solving problems like this, right? I have a problem. As an engineer, I go like do, and here is the solution.
And then you have
chaos. Whereas when it was a problem that couldn't, be structured like that, I kind of throwed it up, in the air and hoped it fall down in a different way so I can look at it from a completely different angle. And many times that helped.
That's so funny. Can we maybe get into your process a little bit? Also, maybe your daily life, some more practical stuff. Actually, let's start. I imagine that tons of your work requires deep focus. You need to sit with a problem. You need to think about it. I would love if you could walk through an example of how do you approach a problem. Do you sit with it? Do you take walks? Do you, listen to music? I'm just super curious if you have a process or any type of, an example of this is a problem, this is how I approach it from a practical point of view. Literally, if I were to try to take inspiration from what you do, can you kind of explain your process in a way where I would go, oh, that's funny, maybe I should try to do something equivalent to that?
Well, I think since, usually, I don't have the luxury to really sit down a whole day and do research, right? I've kind of adopted a way of sitting down maybe for an hour and think about, if it's a really challenging problem that is far from obvious how you solve it, then I sit with it for an hour. And that makes my brain it's gonna, the fantastic thing about the human brain is that it's gonna sit there, right? And don't forget about, how much happens when you sleep. You actually solve problems when you sleep. And in fact, I was surprised quite recently. I dreamt about the problem I was thinking about. And the dream actually came up with a solution that when I woke up, I really remembered what I have dreamt about and could jot it down, and it worked.
What can you explain the dream? Like, what was it? Was it literally you
No,
working with the problem?
I
or was
picked
it
up the problem that I probably had thought about the day before, or something like that. And then I kind of, in the dream, saw a solution to it. But that was, I've never been experienced a thing like that. But I think
that happened recently?
It really proved to me that, I mean, we usually say that sleep on the thing and you'll see the solution. And that's very much true.
Oh, that's amazing.
It's true.
That's amazing. There's a famous mathematician, Srinivasa Ramanujan, who is this weird prodigy mathematician, and he would come up with these absolutely insane conjectures because he didn't have any formal training, and he didn't write down the mathematical proof, but to him, he was like, this is of course correct, like obviously correct. Then 50 years later, we find still that some of his insane conjectures actually turn out to be true. And then he would explain that in his dreams, there was a specific Indian goddess that would come to him and give him the equations, and he would just write them down. It's just...
It sounds like the same thing.
Sounds like the same thing, which is so weird. But something about the power of sleep and dreams. But I also must imagine, in order for that thing to happen to you, that problem must be like really, like you must really care about that problem.
Yeah.
Because if it's like
no, absolutely. Yeah, sure.
Okay, so you sit.
It's important to me to see a solution to it. Yeah.
So you sit with a problem for an hour. Like if it's a difficult problem, you sit with it for an hour.
Yeah, I tell you have to have at least an hour to go deep into something. I mean, that's the whole thing. You cannot. Research is about going deep, right? Deep, and there's just a minimum amount of time for your brain to sink deeply into a problem.
Mm-hmm.
So, of course, I mean, if it's really important for me to make some progress, then I, of course, empty a day and do something about it. But normally, I don't have that time because I'm engaged in so many things, right? So,
annoying.
Well, I mean, it's my own problem because I have the freedom to do whatever I like.
Amazing.
So I'm myself to blame if I'm not happy about it.
Yeah.
So,
what about then? Let me take a big step back here and ask you about mortality. Let me ask you about the fact that all of this stuff comes to an end, or at least it seems like it. We can obviously discuss afterlife and all of that stuff, but it definitely seems like, at least biologically, things end. And do you think about the fact that Pier's life is going to come to an end? That death is a thing that happens. Is that something that you think about, your own mortality and what that means?
Oh, absolutely, I do. Sure. It became actually very real because a year ago I had a cancer.
Whoa.
I got cancer, but luckily, or not good and everything, they wiped it out.
Oh, incredible. Congratulations. That's crazy.
Yeah. So then it was, of course, very close, thoughts, something I thought a lot about. But I've thought about it, ever since I became 60 or something like that, more in the terms of, I remember the first thought I had, well, I'm actually getting to the age when I cannot start big projects that are going to last for 20 years or something like that.
You're like, no!
So I had to adjust to that because, I mean, there were opportunities for me to run a big research center and things like that. And then I asked, if I'm jumping on that train, that's going to be the last thing I do because the longevity of a project like that is of the nature that I cannot do much more. So I started to think about, end of life and things like that. But now I'm thinking more, and probably that was what happened to me when I was sick, that I tend to appreciate more every day when I wake up. it's a new opportunity. One more day, right? Hopefully one more day I'm going to live. And I feel quite energized, and I'm going to do the best I can every day.
That is amazing.
That was not something I thought about, if you asked me 10 years ago, something like that. Oh, what am I going to do in 1 year from now? Things like that. So it's more like focus has moved to, and I think I appreciate life more.
Oh, that's amazing.
Right? That is what has happened. And also, I'm not that scared, as we say, scared to death, but of mortality. I mean, that's a meaning with life that, you should be around for some time, and then some other people should take your baton and continue doing whatever they like, right? And hopefully you have, what is very important to me is that I can, and I feel I can do that, summarize my life, that it has been super meaningful, in all respects, and that I've been kind of useful to add a little bit to our knowledge, and inspired people, and those kind of things are very important to me, to look back and see what did I achieve, right?
Yeah, no, that's completely incredible.
Very important.
I love the fact that there's a greater appreciation of life and more gratitude towards every day.
Yeah. I think more people should think about that.
I love that.
That, you wake up, I have one more day of opportunity, right?
I love that so much.
And I feel very happy when I'm very happy every morning. Yeah.
I just imagine.
I was happy, coming and meet you. Wow, it's going to be an exciting day today.
Yeah, what a strange thing this is going to be.
Many days, it's a day I'm going to meet a new person,
Yeah.
Going to interview me. We're probably going to have a lot of fun. So.
No, that's amazing. Yeah, that's incredible. You can do that. That's there's something fun about. I keep going back to the ancient Greeks. They definitely seem to have something figured out. Where they say that as you get older, generally you go to one of the two extremes. Either you become more bitter towards life and everything there is, or you become more grateful and happy and, wow, this is unbelievable that I get to exist, etc. So it's always fun to figure out what is it that causes one to go one way versus the other. And I do also love the fact that you say that more people should think about death. I'm a huge proponent of keeping death very much top of mind. It's it is, and maybe this is, why do you think you didn't think that much about death in your earlier years? Because it seems like it came to your 60s. Obviously, cancer is tragic in every possible way and hits in a way that I think it's impossible to imagine what that's like if you haven't been there. But why do you think you didn't think more about death and mortality earlier in your life?
Of the simple reason that I think all human beings, when they're younger, they are immortal, right?
Oh, I love that.
They are immortal, right?
I love that.
And so I think that's a simple reason. Then, of course, what I went through a year ago certainly was something that had a big impact on my view of life, of course. I'm super grateful that, they could do something. It seems like they wiped it out, and I'm so thankful for what they can do today that they couldn't do probably 20 years ago.
Yeah, absolutely. That's incredible. That's incredible. Let me ask you, maybe this is going to be a silly question. This is the first time I asked the question, so I'm curious what you're going to be answering here. Suppose you speak to 20-year-old Pierre, and usually the question is, what do you tell him? What does he tell you? When he talks to you and you say, hey man, hey man, this is what I've done. This is what I've spent the last 40 years on. What does he tell you?
What he tells
you. It's not what you tell him. Because usually this is the advice. This is what you should do. What do you think he says when he speaks to you? Do you recall who 20-year-old Pierre was?
Oh, sure. I think I do. Yeah. So should I pretend I'm 20 years old, knowing about the almost 70-year-old pair?
Yes, sir.
What the 70-year-old pair has achieved?
Yes. So,
Okay.
So what is 20-year-old Pierre who looks at 70-year-old Pierre and goes, what is he going to tell him?
So the 20-year-old Pierre was a very insecure guy. He didn't believe in himself.
Oh, wow.
Oh, really not?
Oh.
No. So he would say, I cannot believe that I'm in 50 years is, where you are. How did you start to believe in yourself? That would be the question.
Ah, that's amazing.
Number one question for sure.
That's amazing. What does 70-year-old Pierre reply? What does he say?
Woo. I would say,
Or does he go, you'll
start
find out?
giving yourself credit every morning you wake up that you're actually quite good at things. And that reminds me, so this insecure guy continued to be insecure until he became 40 or so. Very insecure. And
Wow.
I remember that I had to tell myself, you're not that bad, Per.
You're pretty damn good.
You're doing something good. and that also wakes up a memory that is quite strong. I talked to you about my high school and that we're going to have a high school reunion 50 years after the fact that we graduated. Now, the first week of my high school, so I grew up in a small village in south of Sweden, 20 kilometers from the university city Lund. And so I went to high school in Lund and at the science program, and my student mates there, they all came from, most of them came from academic families, and I came from a decent family, but certainly not an academic family with professor in biology or medicine or whatever, right? That was the kind of classmates I had. So I really felt like, someone just threw me into, what am I doing here? And I was the insecure guy who said to myself, no, I cannot stand, I'm not going to be able to survive it. And then I talked to my grandmother, and she said she really loved her grandson, and I loved her back.
Oh, sweet.
Like, she was a role model. She said,
oh, that's amazing.
I always cry.
That's amazing.
You said, Per, it's not going to take so much time until they know who Per Stenström is.
Come on!
That got totally into
Oh,
my
man.
head and gave me so much energy.
Oh, man. That's incredible. Grandma is a freaking beast, man. What
Yeah.
an amazing
Yeah.
person. Wow. Oh, damn. Oh, that's unbelievable.
Fantastic.
Oof. I'm getting goosebumps. I can just feel
No, I mean, that uttering of her has gone back to me many times. Really. Really. That meant a lot. Really, it meant a lot. So I continue. And the rest is history.
The rest is history. Oh, my God.
I'm going to meet these people again, right? In a month or so.
They'll
It's gonna
know
be
who Pierre
so
Stenström
fun.
is.
It's going to be so fun.
Ah, that's incredible. Oh, man. Pierre, we're getting close to 2.5 hours.
Wow. Time goes fast when you have fun.
It's been, I can't believe 2 hours passed. Pierre, this has been genuinely incredible. Literally one of the most fun conversations I've not just had as part of this thing that that's fun to do, but just like generally, what a crazy conversation all over the place, from nitty gritty stuff to philosophical stuff to, and all of it, like all of the 2 hours and change, whatever. I could just feel how present you've been and your enthusiasm, and it's crazy. It's I feel very privileged to have had this conversation with you. It really feels very significant.
Oh, thanks for having me. I mean,
Oh my
it was
God.
awesome for me too.
I appreciate that so much, Pierre. Thank you, everybody. That was amazing, Pierre. Thank you so much. That was so awesome.
Thank you so much, Vidar.